Hi guys, welcome to AP Chemistry. Hope your summer has gone well. We're going to start your summer assignment. I've already emailed you a couple of times and invited you to share a Dropbox folder and given you my Twitter name, whatever it's called. It's PTHS Chem, and so I'm going to try to do some stuff with the Twitter this year. I'm going to use you as the guinea pigs this summer. We'll see how that goes. The PowerPoint presentation that I'm using today, I'm going to upload to the Dropbox folder so you can print the PowerPoint off if you want to use it to follow along with, or you can just listen and watch, and then I can get you copies made when school starts again. Okay, so we're going to move to the first part of the gas laws. I think you're going to find this is pretty doable, and it's not going to take us a lot of work over the next 3 or 4 weeks. It'll just get us in good shape to start the semester. Okay? Alright, we're going to talk about characteristics of gases, and we have already talked about that. You know that there are some things that are pretty true about gases. You know that they have no fixed shape or volume, that they expand to fit the shape of their container. You know that they're easily compressible, and the reason that they're that way is because there's lots of empty space between those gas particles, whether they're molecules or atoms. And so because there's lots of empty space between them, we can press them really close together. Also, because there's lots of empty space, they have really low densities. There's not a lot of mass compared to the volume that they have. So you'll remember that the calculation or the equation for density is the mass divided by the volume. Okay? We're going to use that here in just a few slides. Alright, in addition to that, there are 4 properties of gases that we use to define the state of a gas, to describe its behavior and its characteristics. The first of those is the quantity of the gas. And when we talk about quantity in the past, we've talked about that as moles. And so that's a term that you're familiar with. We haven't necessarily used the symbol to describe moles, and that's a lowercase m. The second thing that we use to describe gases is the temperature of the gas. And temperature has an SI unit of Kelvin, and even though we measure in Celsius in the laboratory, all of our calculations for gases are going to be done in Kelvin. Okay? The reason that we do that is because we don't want any negative temperatures involved in our calculations, and all Kelvin temperatures are positive values, and you'll see some examples of that as we work some problems about why that's necessary. The third property that we're going to talk about is the volume of the gas, and you know that volumes can be changed very easily. For a gas, we can squeeze it really small and put it in a really small container, or we can open that container and let it spill to fill the size of the room. The unit that we use typically to describe volume of gases are liters. We'll also talk about them in milliliters and sometimes cubic meters. But typically as a chemist, you're going to use liters to discuss the volume of a gas. The symbol that we use for volume is a capital V. The last characteristic of gases, and actually the first one that we're going to talk about, is the pressure of a gas. And we usually measure pressure in atmospheres, and we abbreviate that ATM. I think I mentioned that to you last year. It's not the only unit that we use for pressure, and so I'm going to introduce you to some of the other units that we use, and we're going to look at some conversions between them. Okay? Those 4 quantities are what we're going to work with to start. Let's talk a little bit about pressure and show you some ways to move between units of pressure, and then we'll talk about some things called the empirical gas laws. Alright, by definition, pressure is described as the amount of force applied to a unit area. And when we talk about atmospheric pressure, which is the pressure of the air around you, that's the weight of the air pressing on the surface of the earth, and it's a very specific measurement. So we talk about a column of air that's a 1 meter by 1 meter column. Okay, so if we could draw a 1 meter by 1 meter square on the surface of the earth and then measure all of the air that sits above that 1 meter squared, area, then that's how we're going to calculate our atmospheric pressure. Okay? There's a lot of air there, believe it or not. That's a pretty big mass, and so the force that it applies to the surface of the Earth because of gravity is a really large force. Okay? So when we talk about atmospheric pressure or barometric pressure, we're talking about the pressure of the air pressing on the surface of the Earth. And meteorologists use those terms a lot to discuss what's going on outside in terms of the weather. All right, so we'll talk a little bit about that as well. When we talk about gas pressure, we typically talk about it in about 4 or 5 different units. And the first of those is the unit Pascal. It's named after the scientist Blaise Pascal, and that's the SI unit. And a Pascal is identified or is equal to 1 Newton of force per 1 meter square of area. Okay? Newtons are the unit of force measured in SI units. Well, pascals are not nearly as usable for us as chemists, and so we tend to use some other terms. One other term that we can use is a term called a bar, and a bar is the equivalent of 10 to the 5th or 10,000 pascals, and that's equal to 100 kilopascals. So you remember that kilo is 1,000. So if I have 10 to the 5th pascals, and I know that 1 kilopascal is 1,000 pascals, then that's where that 100 kilopascals comes from. Okay? Bars we don't typically use in chemistry. You'll see them some in some of these exercises, these problems that we work. That's typically a meteorology term. So if we were to go to the National Weather Service website today and check the atmospheric pressures for today, you would see that those units would be measured in millibars. Okay? We tend to use a couple of other units, and the units that we're going to use are atmospheres of pressure. We're going to talk about millimeters of mercury, and we're also going to talk about torr. All right? Those are the ones that we're going to use most often. Okay, so let's talk about how we measure that pressure. We measure pressure using something called a barometer. And the picture that you have in front of you is a very simple barometer. And a barometer is just a column of mercury that's elevated in a glass tube inside a bowl or a dish of mercury. It's a really simple machine instrument to use, I guess. What we know is that if we take mercury, which is really dense and really, really heavy, and put that in a bowl, and then invert a glass column with a closed end, and so you'll see this top end is closed on one end, and then an open end on another, it acts just like a straw does when you put it in a glass of liquid. You know that when you put that straw down in the liquid liquid flows up through the straw to a certain height. Well, the mercury does exactly the same thing in that glass tube. If we have that glass tube pumped out so that it has absolutely no air or anything in it before we invert it, that's called a vacuum, and that's what you see labeled at the top of that tube. Well, when we invert that glass tube in that dish of mercury, some of that mercury is going to rise up in that glass. And it's going to depend upon what kind of pressure is being exerted from outside the glass and from inside at the surface of the mercury. So when we talk about atmospheric pressure, we're talking about the force that's being applied to the surface of that mercury in that dish. If there's a lot of air pressure, because there's a lot of air, then it's going to push really hard on that mercury, and that mercury has to go somewhere. And so it stands to reason that if we push down on the mercury in the dish, the level of the mercury inside the tube is going to rise. Okay? If we reduce that pressure on the surface in the dish, then because we're not pressing on that surface so much in the dish, then that level of mercury in the tube is going to go down. Well, what a man named Evangelista Torricelli recognized was that if we can look at the difference between those two heights of mercury, then we can equate that to the amount of atmospheric pressure that's caused by the air pressing on the surface of the earth. So we have a measurement called a torr, and a torr is named after Evangelista Torricelli, who has a great name. Torr is another one of those units that's one of my favorite chemistry terms, just because I like the name of the guy that invented it. But we measure atmospheric pressure in torr. All right. We also measure that in millimeters of mercury, and you're more likely to see the millimeters of mercury for us as chemists than you are to see the torr. But they're equivalents. What we know is that 1 torr is equal to 1 millimeter of mercury. Okay? What we also know is that those torr and those millimeters of mercury are equal to atmospheres. So we know that 1 atmosphere is equal to 760 torr. It's also equal to 760 millimeters of mercury. All right? So if we can have that column of mercury, we can measure our barometric pressure, and that's exactly how a barometer works that measures our atmospheric pressure. Now the question then becomes, well, why do we use mercury? Couldn't we use some other kind of liquid? Couldn't you use water or alcohol or vegetable oil? And the answer is yes, you could use any of those. But we want to think about the density of this material, how close it is together, and the amount of force that it takes to push on the mercury versus the amount of force it would take to push on a column of water. I have seen barometers that are water barometers. One of the universities that I've either visited or worked at, I don't remember which one, at one time had a water barometer. The difference between the 760 millimeters of mercury and a water barometer is that it's going to take about 30 meters of water for that, I'm sorry, not 30 meters, 30 feet of water for that barometer to work in the equivalent way that the mercury barometer was. So that's why we use mercury, because it's so dense we don't have to use nearly as much of it. Okay? Okay. One last term that we want to define before we move on, and that is the term standard pressure. Standard pressure is defined as the atmospheric pressure at sea level, and it has a standard, which is why it's called that. It has a standard value of 1 atmosphere. Okay, so that 1 atmosphere, that value is going to be really important to us. We're going to use it a lot. We're going to talk about something called standard temperature and pressure, or STP. And so standard pressure for us is always going to be considered to be 1 atmosphere, which is 760 torr, or 760 millimeters of mercury, or a lot of times we use this term, 101.325 kilopascals. Okay? All right. So keep that in mind. Now, if we want to measure the pressure of a gas in a container, okay, not necessarily our atmospheric pressure, but the pressure of a gas in a balloon, or of a container that's got a fixed volume, like the glass container that you see in the diagram. We use an instrument called a manometer. And a manometer is really very simple. It's just a gas container with a very long neck on it, and the glass tube on it is turned so that it looks like a U. Okay? There's a valve on the gas container that we can open and close with a stopcock, and then the other end of that glass tubing is open to the atmosphere. Okay? So we evacuate that glass container and we pump it full of a specific gas and close off the valve on it. And then we add some mercury to the tube. And it doesn't have to be 760 millimeters of mercury, because what we're going to do is look at changes in height. to help us look for the pressure of that gas. So we're going to add that mercury in. That mercury should get to a level, if this has all been evacuated, that should be at an even level on both sides. But as soon as I open up that stopcock and let that gas flow out of that closed container, that gas is going to start pushing on that mercury. And depending on the pressure of the gas, how much force it has in that area, it will either push that column way down, and so that we'll see one side is much higher than the other, this direction, or it could be that that gas doesn't exert a whole lot of pressure and we might get some levels that look like this and this. Okay, when we measure those heights of those two columns of mercury from the base, then we can either look at the addition of those or the difference of those to measure our pressure of our gas that's in our container. Okay, so that's what a manometer does. Okay, so let's look at a couple of examples. Let's start here. And let's say that the pressure of a gas is measured at 49 torr. And I want to know, what is that pressure in millimeters of mercury, in atmospheres, in Pascal, and let's just go ahead and do in bar as well. Okay, so it's back to factor label again. I know you're excited. Let's start out and set this up. So we know that 49 torr, we have a conversion that 1 torr is equal to 1 millimeter of mercury. And I know what you're saying. That's really easy. I shouldn't have to write that conversion down. I know you think it is, but I'm going to go ahead and show you that setup so that you can see it. Because for some of you, you need to have a little bit of review. Okay? So we know that 49 torr then is equal to 49 millimeters of mercury. And you'll notice that I'm going to keep the same significant figures. There are 2 significant figures to start this problem. I'm going to finish with 2 significant figures. Okay? Now, I know that there's 49 millimeters of mercury, and I want to convert that to atmospheres. So I know that 1 atmosphere is equal to 760 millimeters. Whoops, put that in the wrong spot. Sorry about that. 760 millimeters of mercury are equivalent to 1 atmosphere. And so if I divide 49 divided by 760, I get 0.0644736842. Still, rounded off to 2 significant figures. So I'm going to round that off to 0.064 atmosphere. Okay? Now, I still want to know how many Pascal that is. So I'm going to take that 0.064 atmospheres, and I'm going to convert that to Pascal. And I know that 1 atmosphere is 101.325 kilopascal. Okay? And for whatever reason, I never remember the conversion for pascals, but I do remember the version for kilopascals. But it doesn't matter because I know what kilo means. So I know that 1 kilopascal is 1,000 pascal. So again, I can do my math. I'm still going to have 2 significant figures as my answer. So 0.064 times 101.325 times 1,000, and I'm going to get 6,500 Pascal. Okay? I also want to know how many bar. So I said that 1 bar is equal to a certain number of pascals, right? And of course, I don't remember that one because it's useless to me. I never think about it. But I know that 1 bar is about 10 to the 5th, 10 to the 5th pascals. So if I start with 6,500 pascals, and I say that 1 bar is 10 to the 5th pascals, then 6,500 divided by 1 times 10 to the 5th is going to give me 0.065 bar. Okay? And so as long as you can keep those conversions where they're handy, you can move back and forth between those fairly easily. Okay? So good reminder for you about conversions. You're going to have to do some of them for homework for me. Okay, so let's try another one. Now let's rank a set of pressures. And so let's rank these in decreasing order. And let's see. Let's start with 75 kilopascal. And let's go with 300 torr. I'm going to put a decimal place there. That tells you I've got 3 significant figures there, right? Let's try 0.60 atmospheres. And 350 millimeters of mercury. Okay, so I've got 2 values there with 2 significant figures and 2 values with 3. Well, for me it makes more sense to put everything in atmospheres. I know that atmospheres are really the standard unit that I'm going to use for a chemist, even though that is not the SI unit. It's typically the one that we're going to use, and so that's the one I'm going to work with. So if I start with these and I convert 75 kilopascal to atmospheres, I know that 1 atmosphere is equal to 101.325 kilopascals. And when I check that with my calculator, which I'm doing right now, I should get somewhere around, I got a mistake, that won't work, will it? 75 divided by 101.325 gives you about 0.74 kilopascals. And that should make sense to you because 75 out of 100 is 3/4, right? And not kilopascals, it should be ATM. Okay? And if I take 300 torr and convert that to atmospheres, I know that 1 atmosphere is 760 torr, and so 300 divided by 760 is 0.395 atmospheres. I'm going to have 3 significant figures there because of that decimal place after the 300 on the torr. Okay? Then I've got 350 millimeters of mercury, and again there are 760 millimeters of mercury in 1 atmosphere. And so 350 divided by 760 is about 0.461 atmospheres. Okay? So if I'm going to rank these in decreasing order, then 75 kilopascal is greater in pressure than 0.6 atmospheres, which is greater in pressure than 350 millimeters of mercury. Of course, I've run out of room, which is greater in pressure than 300 torr. Okay? And that's our answer to that question. I'm going to caution you now, because it will make it a whole lot easier for you and me both, and then for you as you get ready to take the AP test, if you'll start putting boxes around answers as you finish them, okay? And for those of you all who don't like to show me your work, get used to it. You've got to do that for me in AP Chemistry, okay? Okay, so we've just got just a few more laws to talk about, and this is not going to take very long. We want to talk about some laws called the empirical gas laws. And we used that term empirical last year. And I wonder if you remember what we talked about in terms of empirical formulas. We talked about empirical formulas. We talked about that being the smallest whole number ratio, the simplest form of a chemical formula for a compound. Well, that term empirical comes from observation. So when we talk about empirical gas laws, those gas laws have been developed because of lots and lots and lots of observation of gases and the way they behave relative to one another. Okay? Here's what we know about the gas laws. We know that if we have a certain amount of gas, and we're going to go with moles, we've got three other characteristics that we can talk about in terms of that gas. We've got the pressure, the volume, and the temperature. Okay? And so if we talk about pressure, volume, and temperature of those gases and changing one of those properties, can't write, those will affect a second property as long as the third remains constant. Okay? Now what that means is, in terms of an example, if I maintain the temperature of a gas and I keep it at a constant, say room temperature, and I apply pressure to that gas, the volume of that gas is going to change relative to the pressure change. Okay? Just as long as I don't change the temperature. Or I could not change the pressure, keep it at a constant pressure, and heat it up, and that's going to affect its volume. Or cool it down, and that will affect its volume. Okay, so when we talk about the empirical gas laws, we're going to assume that we've got a certain amount of gas. We're going to hold one of its variables constant, and then we're going to make changes to another one and see what happens to the third. And that's all the empirical gas laws do. We call them plug and chug problems because the equations are very easy and the calculations are very easy. Gas law number 1, Boyle's law. Boyle's law says that the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. And that should make sense to you. So you think about if we have a balloon that has a certain volume and a certain pressure, and it's got a certain amount of air in it. That air is not going to change, and it's just at room temperature. So we've got a fixed quantity and we've got a constant temperature. Well, if I squeeze on that balloon, that is, I increase the pressure on that balloon, what's going to happen to the volume of the balloon? It's going to get smaller, right? And then if I let go of the balloon, then the balloon is going to expand. So what we know is that pressure is inversely proportional to volume when we have a constant temperature. Okay? So we use an equation to describe that. Okay, so if you look at this slide, we've got a couple of plots of volume versus pressure. In the plot on the left, we've got pressure on the x-axis and volume on the y-axis, and you'll see that as the pressure is increasing as we move from left to right, that the volume is decreasing. Okay? And so if we collect data from a gas in a balloon and we increase the pressure on that balloon, we should see the volume go down. Well, if you look at the plot on the right, it's still a plot of volume and pressure, but this time our x-axis is the inverse of the pressure. And what you see then is as the pressure increases, then the volume is, or I'm sorry, the inverse of the pressure is increasing. You'll also see that the volume is increasing. And this time is a linear relationship, okay? Well, what we know is that if we multiply the pressure times the volume of a gas, and we've fixed its temperature and its quantity, we should always get a constant value. And so we write that as PV is equal to K, some constant, okay? And that's going to depend on the gas, and it's going to depend on the temperature and the amount that we have, okay? That was Lucy that you hear barking. She wanted to say hi to you. The equation that we use to describe Boyle's law is a really simple equation, and that is that if we have a gas at a fixed temperature, the equation that explains that gas is P1 V1 has to be equal to P2 V2. Okay? Both sides of that equation are equal to that constant K. And so it doesn't matter what the pressure is, there must be some volume at that pressure that's going to give us that K value. Okay? So if we see that pressure change, then we can calculate what the volume change is. Alright? So that equation, P1 V1 is equal to P2 V2, is going to be a really important equation for you to remember. Okay, Charles' law, instead of looking at the pressure and the volume with a fixed temperature, looks at the volume and the temperature and a fixed pressure. Okay, so Charles' law says that the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. Well, you know what's going to happen. If I have a balloon and I heat it up, it's going to get bigger. And if I have that balloon and it cools down, it's going to get smaller. And so we get that same kind of idea as we did with the Boyle's law. But what we now know is that volume and temperature are directly related. Okay? So the way that we write that equation for Charles' law is V1 over T1 is equal to V2 over T2. So I've got that in a different color. I'll put a different colored box around that one. That equation is going to be important for you to remember too. You may like to write this equation a little bit differently. You might want to write it as V1T2 is equal to V2T1. Exact same equation. I've just cross multiplied. Okay? I remember the equation in the box. You may remember it more easily if it's written the way it's written in blue. Either way is fine. You'll just want to keep it in mind because it's one you're going to need. Okay, so now if we look at a plot of volume versus temperature, we see that this time as temperature increases across the x-axis, we see the volume increasing along the y-axis. So in the Boyle's law plot, we saw that the plot of V versus 1 over P is linear. Well, for this one, it's V versus T is linear, okay? So the change in V over the change in T this time becomes our slope, and that's going to be equal to our constant, okay? So if I know that V and T are equal to a constant at one volume and temperature, then at another volume and temperature, I must be able to get that same K value, okay? So that's where the V1 over T1 is equal to V2 over T2 is. Write that down again. V1 over T1 is equal to V2 over T2. And that's Charles' law. And you're going to have to come up with a way to remember these. The way that I remember Boyle's law is that things boil at a high temperature. So temperature should be part of that equation, but it's not. It's the opposite, and that's how I remember that. I don't know how you're going to remember Charles' law. You'll come up with something, though. I know you're very talented at doing that. All right, so here we go with one more. Here's your favorite person, Avogadro. And yes, it's the same Avogadro. And it talks about 1 mole of a gas, typically, when we talk about gas laws. So 1 mole of a gas, you know, is 6.022 times 10 to the 23rd particles. Well, Avogadro's law says that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of gas. So you know what that means. The more gas we have, the more space it takes up. Okay, if we hold the pressure and the temperature constant, we're not changing either of those two variables, then as we add more gas in, it has to take up more space. Okay, so what that means is that when we look at a plot of the volume versus the number of moles, as the number of moles increases, we're also going to see the volume increase, and so we get that nice linear plot there again. Okay, the equation that we use for this then is V1 over N1 is equal to V2 over N2. Gay-Lussac's law, or I'm sorry, not Gay-Lussac, Avogadro's law is a law that we don't use a whole lot in terms of empirical laws. We're going to see the relationship between volume and moles, but we're not going to work as many problems with just those two variables being affected as we will with some of the other stuff. Okay? Now, there's one other law that I want to talk to you about, and that's a law that's called the Gay-Lussac law. And Gay-Lussac gets avoided or ignored a lot of times, but it shouldn't. Gay-Lussac law says that a specific quantity of gas at a fixed volume has an increasing pressure when temperature is increased. Again, that should make sense to you. If I have a certain amount of, I don't know, say aerosol hairspray in a container, like a hairspray can, and I heat the hairspray can. There's my hairspray can. Okay, heat it up. What's going to happen to it? You know, boom, right? The gas is going to increase the pressure until it's going to cause the can to explode. So what we know is that pressure and temperature of a gas, when the volume and the quantity are held constant, are directly related. The higher the temperature, the higher the pressure. If I increase the pressure so much that the container can't handle it, the container is going to explode. Okay? So we know that the equation for that then is, the plot for that we're going to see is going to be, if we are increasing the temperature, what's going to happen to the pressure, and we're going to see that increase. We're going to get that nice linear plot again. We're going to get that P is equal to some constant K times T. Okay, K is going to be our slope again, or we're going to get P over T is equal to K. And then the equation that we're going to use for Gay-Lussac law is P1 over T1 is equal to P2 over T2. Okay, and there's Gay-Lussac. Alright, so we've got four empirical laws. We've got Boyle's law, which looks at pressure and volume with a constant temperature. We've got Charles' law, which looks at volume and temperature with a fixed pressure. We've got Gay-Lussac's law, which looks at pressure and temperature with a fixed volume. And all of those are for a specific amount of gas. And then we have Avogadro's law, which says we're going to keep the pressure and the temperature constant, and we're going to see what happens when we increase the amount of moles of gas, which is going to show us an increase in volume. Okay? Now, that's all really great, and that's four different equations for you to remember. But I can make it a little bit easier for you because we can take all of those conditions and change them all at the same time if we want to. And if we do that, then we can use an equation called the combined gas law. So let's look at that. Combined gas law, there I am with red pen again. Combined gas law takes those, at least 3 of those 4 equations. We could include Avogadro's, but it takes Boyle's, Charles, and Gay-Lussac law and puts those 3 together in an equation. And that equation is really nice. It's P1 V1 over T1 is equal to P2 V2 over T2. And those are at a constant number of moles. Okay. When that happens, we can use one equation to remember all 4 of those, because you think about it. If any of those 3 equations, Boyle's, Charles, or Gay-Lussac, are used, one of the variables has to be constant. Okay? So, let's assume that we have a gas where the temperature is held constant. Well, if the temperature is constant, T1 and T2 are equal to each other, right? So if T1 and T2 are equal to each other, and I want to solve this particular equation for one of the P's or one of the V's, then if we cross multiply and we do the algebra to get one unit or one variable isolated, what we find out is that the T1 and the T2 will cancel each other out. Okay? So any variable which is held constant is going to cancel out of combined gas law, which is nice, because then all you have to do is remember combined gas law instead of trying to remember Boyle's and Charles and Gay-Lussac and Avogadro. You get too many more equations to keep in your head and your head will explode. So I don't know who came up with combined gas law, but they were brilliant, and it's only because I've been doing this for so long that I can tell you all 4 of those laws. If I were learning this again, I would say I'm just going to learn combined gas law and work from there. So you're welcome. All right, let's look at some examples of empirical gas law problems and what you're likely to see in your homework. Okay, this first exercise says the sulfur dioxide gas forms acid rain and is produced in the exhaust of automobiles and power plants. A 1.53 liter sample of SO2 at a pressure of 5.6 times 10 to the 3rd pascals undergoes a pressure change to 1.5 times 10 to the 4th pascals. If the temperature is constant, what will be the new volume of gas? Okay, so you guys need to get used to the fact that problems are going to start adding extra stuff, like what the compound is used for or where it's produced. And so learn to mark out the stuff you don't need. Okay, so that first sentence we absolutely don't need. We're done with that. It's great that it forms acid rain, but it's not part of the problem. Okay, now this is the way I set these problems up every time I work them. You've heard me say that before. Every time I work a problem, I set it up the same way. Gas law problems are much easier if you'll do the setup first. I know what some of you are saying. I don't need to do that, but trust me. Okay, so I'm going to go through and I'm going to find all the numbers and I'm going to attach a variable to those so I know what they are. So the first thing that I see is a 1.53 liter of sample. That's volume 1 is 1.53 liters. Okay, and the next number I see is that sample is at a pressure of 5.6 times 10 to the 3 pascals. That's my pressure 1. 5.6 times 10 to the 3rd pascals. Okay, it says it undergoes a pressure change. That's my P2. That's 1.5 times 10 to the 4th pascals. And it says if the temperature is constant, so that's not changing, I don't have to worry about the temperature. What will be the new volume of gas? V2 is what I'm looking for. Okay? If I look at that, I know that I'm looking for P1 V1 is equal to P2 V2, and that's a Boyle's law problem. So I'm going to write this. P1 V1 is equal to P2V2. And I'm going to solve for V2 before I ever put any numbers in. So I'm going to divide both sides by P2, and when I do, I get V2 is equal to P1V1 over P2. Okay? And now I'm going to be able to substitute my numbers in and get my answer. Before you do that, though, start thinking about these problems in terms of what makes sense. So we said that pressure and volume are inversely related. That means if one goes up, the other one has to go down. So look at your pressure. Did the pressure get bigger or did the pressure get smaller? Well, from 10 to the third to 10 to the fourth, the pressure obviously got a lot bigger. It means we're pressing on the sides of that container much harder than we were before. So if we're pressing harder, we're applying more pressure. What should happen to the volume? It should get smaller. Your number, the answer that you get, should reflect that. And if it doesn't, something's gone wrong. So let's put the numbers in and see what happens. So P1 is 5.6 times 10 to the third pascals. And V1 is 1.53 liters. We're going to divide that by P2, which is 1.5 times 10 to the fourth pascals. And we should be able to get an answer. Now, here's the question. What should your units be for your new volume? Well, they should be liters, right? That's what our volume is in our first part of our problem, so that's what our answer should be in. And what happens to pascals? We've got one in the numerator, one in the denominator. They cancel out. Okay, so when you do the math for this, we get V2 is equal to 5.6 times 10 to the third times 1.53 divided by 1.5 times 10 to the fourth, and I get another error. I don't know what it is I'm doing while I'm working these problems with you guys. There we go. I get 0.571 2 liters. Okay, well, look at your significant figures. How many significant figures do you have here? 2. How many here? 3. How many here? 2. And so your significant figures need to match the least number of significant digits in your parts of your problem. And so our answer needs to have 2 significant digits. So I'm going to round that off to 0.57 liters. Okay? Remember what I told you earlier on to put a box around your answer so I can see it easier. Okay? They're just plug and chug problems. And so we said that the volume should get lower, and our math proves or shows that that happens, and so we can stop this problem and say we've done this exactly right. All right, here's another problem, and then I'm going to stop after this one, and it'll be your turn to do some practice. So this one says an ideal gas is contained in a cylinder with a volume of 500 milliliters at a temperature of 30 degrees Celsius and a pressure of 710 torr. The gas is then compressed to a volume of 25 milliliters and the temperature is raised to 820 degrees Celsius. What is the new pressure of the gas? All right, I don't have any extras in this problem, so I'm not marking anything out, but I am going to label everything. Again, I work every problem exactly the same way. So the first number that I see is 500 milliliters, and I know that that's a volume. And I also notice that there's a decimal point after that last 0, so that means that that thing has 3 significant figures. Okay? There's also a temperature of 30 degrees Celsius, so that's my first temperature. Okay? And a pressure of 710 torr. Again, there's a decimal place after that, or a decimal point after that 710, so I know it's got 3 significant figures. Okay? That's the first set of conditions that I have. All right, then it says the gas is then compressed to a volume of 25 milliliters. And now I just have 2 significant figures. And the temperature is raised to 820 degrees Celsius. Still, just 2 significant figures. Then it says, what's the new pressure of the gas? I'm sorry, that should be T2. This is P2, and that's my question mark. Okay? I have nothing that stayed constant here. Everything is changing, so I'm going to have to use the combined gas law to do that. But that's an easy one to remember. It's going to be the P1V1, P1V1 over T1 is equal to P2V2 over T2. Okay? I'm solving for P2, so I'm going to rearrange the equation before I do anything else. All right? You need to work through the algebra and make sure that this works. But I'm going to end up with P2 is equal to P1 V1 T2 over T1 V2. Trust me, but check just to be sure. All right? So now it looks like I'm ready to plug numbers in. But remember when I told you about the quality of temperature that we use, the characteristic that we use to describe gases? Temperatures have to be in Kelvin, okay? What would happen if that were a minus 820 degrees Celsius instead of a positive 820 degrees Celsius? That would give me a negative pressure, and that's impossible. You can't press anything farther down than to 0 degrees or 0 torr, okay? So if we have a negative temperature, everything's going to be the opposite of what it should be in terms of sign, and that's not possible. So we need to have that always be a positive value, and to do that, we're going to turn this we're going to change it to the Kelvin scale. So I'm going to add 273 to both of these, and it's actually 273.15. But we're close enough with the 273 when we're doing gas law problems that that's enough of a change for us. Okay? So this becomes 303 Kelvin. Now we've got 3 significant figures. Not going to make a difference to us because we've got 2 for the volume over here. And so our answer is going to have to be 2 significant figures. And then if we do 820 plus 273, we get 1093 K. It's hot. Okay? Now I'm ready to plug my numbers in. So I'm going to put in 710 torr. What's happened to my pen? There we go. 710 torr times 500 milliliters times our T2, which is 1093 K. And we're going to divide that by our original temperature, which is 300 Kelvin, and divide by our volume 2, which is 25 milliliters. And that's 2 significant figures, so our answer is going to have to be 2 significant figures. So 710 times 500 times 1093 divided by 303 and divided by 25. And I get 51,223. That is really gigantic. It doesn't seem like it's possible. But look, I've gone from a volume of 500 milliliters all the way down to 25 milliliters, okay? And I've raised my temperature a whole lot. So because I've raised that temperature so much, those gas particles are moving a whole lot. They're bumping into the walls of that container. That's increasing the pressure, okay? So even though that volume went way down and that pressure went way up, I'm going to have a really big, the temperature went way up. I'm going to have a really big pressure. Well, if I want that to be 2 significant figures, the easiest way for me to turn 51,223 into 2 significant figures is to write that as 5.1 times 10 to the 4th. And that's going to be torr. And again, put a box around it so I can see it easier. Okay? So, that's the first part of your lesson, is converting pressures from one unit to another, and then using the empirical gas laws and being able to determine the change in a variable based on other changes. All right? So now you're ready to start your homework. Good luck. Email me if you need any help.